Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous video, we said that in a log model with a dummy variable, the coefficient represents a percentage difference between the groups. So in this video, we'll see the derivation of the formula, which is something that we have already introduced in the previous video where we talked about the log level model. This is exactly the same, so the dummy variable will be considered as like a variable at the level. So the interpretation and the formula that you'll see will be no different from the formula that we've seen for the log level model. But let's put it into practice and see exactly how the derivation starts or derives from the simple model with a dummy variable. And we're going to start with the usual model where we've got ln of y equal to beta 0 plus beta 1d and an error term, assuming there's no correlation between the dummy variable and the error term. And the expectation overall of ln y on d would be equal to beta 0 plus beta 1d. This is what we have also seen notation-wise in the log level video, and that's why I've decided to go a little bit quicker on that. The only part where now you'll see a slight difference from that previous video is that just like we have worked so far with the dummy variables, we'll have case 1 where dummy is equal to 0, and then we'll have a case 2 where dummy is equal to 1. And from here, you can very clearly see the path that we're trying to take. So for K0, where D is equal to 0, then ln of Y0 is basically your beta 0. While for D1, your ln of Y1 is equal to beta 0 plus beta 1. Which means that if you are trying to subtract and find the difference, so ln of Y1 minus ln of Y0, then the difference is clearly this beta 1. From here on, just like we did when proving the log level model, we're going to use the log properties, which means that from here we can use and rewrite these as ln of the ratio of y1 over y0 is beta 1. From here, then by exponentiating, we're going to have that y1 over y0 eats the e to the power beta 1. Okay, and obviously, if you want to solve for percentage, just like we've done before, you're going to have the fact that the percentage difference is just y1 minus y0 divided by y0, which is simply e to the power beta 1 minus 1. And finally, as a percentage, this would have been multiplied by 100%. So also this we multiply by 100%. So nothing new. Interpretation, very clearly the same things we've seen in the log level model is that the coefficient beta 1 gives the exact percentage difference between the two groups. So if in the log level general model that we had, we looked at like if the y increases if the x increases by 1 unit, in here we have the x, your d, going from 0 to 1, so switching groups from no to yes. The same rules that we have learned in the log level model will apply also in here, which means that for small beta 1s, the e to the power beta 1 minus 1 will be approximately simply beta 1. So that's why saying that the interpretation is 100 times beta 1 is a good approximation. Okay. So what we've done in here is by using logs, we've turned multiplicative differences into additive ones, and then exponentiating them brings us back to the percentage changes. The key takeaway in here should be that nothing has changed from what we've learned in the log level models. In here, this is just a log model with a dummy coefficient, which translates into a percentage difference using, again, the same formula that we have been introduced before. In the next video, we'll apply this formula in a worked example and compare the approximate and exact percentage differences so that you can see that you're adding no new information to what you've learned in your log level model. So stay tuned, and I'll see you in the next video.